Hello and welcome to the Math Lounge, where I go to enjoy a cup of tea surrounded by my mathematical toys and games. Anyway, today we're going to be talking about areas in polar coordinates, and so let's get right to it. Starting out, we need to remind you about, or I need to remind you about Riemann sums. So in rectangular coordinates, you know that a Riemann sum would be made up of rectangular chunks that you put together to make an area. So if we translate that idea to polar coordinates, those Riemann sums would not be rectangular chunks, but would be little pi wedges, as you see here in these four diagrams. The top left diagram that looks sort of like a seashell is made up of, you can see the area could be approximated by um, a bunch of little pi wedges. Same thing goes for this propeller. And then the blob in the bottom left has a bunch of pi wedges. I have the same blob next to it. I don't know how many pi wedges I used in the bottom left. Maybe it's 30. But in the bottom right, there's about 200 pi wedges. So they're so small that you can't see them very well, but they are there. At any rate, to understand area in polar coordinates, we need to understand the area of a sector. A sector is just a piece of a circle, and that's what those areas or those Riemann sums will be made up of. So eventually we'll use this to develop our formula for area in polar coordinates. So here's the area formula for a sector. It's 1/2 times the angle times r squared. And so the way that this is going to translate into polar coordinates is this. In fact, let's see if I can write this down. So we have the area of a sector. Okay, I finally got my Apple Pencil to work, and so the area of my sector is theta over 2 times r squared. And so what we would do to find a formula for your area in polar coordinates is to recognize that what we're going to do is we're going to add up a bunch of these. So delta theta, so you have to imagine that we've divided our whatever region it is into little pi wedges, and these pi wedges are each delta theta, delta theta, delta theta, and then we're going to add them up. And remember that r is equal to a function of theta. And so this thing turns into the integral of f of theta squared over 2 times d theta. So hopefully this is at least somewhat familiar to you, this idea that when you use the fundamental theorem of calculus, the Riemann sum turns into an integral, and you're able to compute the area using an integral instead of a Riemann sum. At any rate, let's get back to this. Oh, that's not what I want. So here's our formula for area in polar coordinates. The alpha and the beta come from the whatever angles we're starting and ending at, and then we'll work from there to do this. So here's some examples. I want to find the area inside this curve. This is a cardioid or a limacon. So let's see, I'll just move this up and we'll make some room here. Okay, so first things first, f of theta, f of theta is 2 minus 2 cosine of theta. Now, since we're doing that inside the entire cardioid, I'm going to start at 0 and end at 2 pi. So that's one full circle. We're going all the way around the loop. And then what else do we need to know here? I think that's it. So now all that's left is to do the integral. So my area is 1/2 times the integral from 0 to 2 pi of 2 minus 2 cosine of theta squared all over 2 d theta. Now, if you're looking at that thinking that's going to be painful to do, you're right. But don't fret. I've got a few tips and tricks for you. First off, oh, I've got too many 2's. There. I only need the 1/2 in one place. Out of habit, I put it inside the integral, but generally the book has it outside the integral. Sorry about that. Anyway, so let's go ahead and square this thing. So 1/2 times the integral from 0 to 2 pi of 4 minus 8 cosine theta plus 4 cosine squared theta. Okay, so we have that. Now we're going to use the power reducing formula for cosine, which says that cosine squared theta, just a minute, 4 minus 8 cosine. Okay, so cosine squared theta is 1 plus cosine of 2 theta over 2. So this is, let me just scroll down here and, well, let me scroll. I can't go up any further. Here's what I'll do. I'll zoom way in, and I'll put these right here. That the cosine squared is 1 plus cosine of 2 theta over 2. So these are formulas that you should know from Calculus 2, but you might not remember. And then sine squared theta. Actually, they're from trigonometry. They're from high school. 1 minus cosine of 2 theta over 2. Let me make sure I got that right. Yeah, that's right. Okay, so there's my two power reducing formulas that are super handy for this section because of the whole square business. Anyway, getting down here, the rest of this is pretty straightforward. You're just going to execute the antiderivative. So I'll talk through it, but it's not going to take much effort. 4 theta, because the antiderivative of 4 is theta. Antiderivative of cosine is sine. The 4 and the 2 I'm going to cancel, so I'll just get a 2 here, times the antiderivative of 1 is theta. The antiderivative of cosine 2 theta is sine 2 theta over 2. And that's it. So now I'm going to go from 0 to 2 pi. So now we're going to plug and chug this thing. So the area is 1/2 times 8 pi minus 8 times the sine of 2 pi is 0, plus 2 times 2 pi plus sine of 4 pi is 0. And then 1/2 of, I think this is all going to be 0 because the sine is of 0 is 0. Make sure you at least make an effort to think about the lower limit if it's 0, because cosine of 0 is not 0. At any rate, what are we doing here? We have the area is 1/2 of 12 pi, so that's 6 pi. Boom. All right, so a lot of effort for this particular area. Let's go on to the next problem. We want to find the area inside this curve. Now this curve is different from the one we just looked at because you've got all these loops. So there are two options to do this. One is that we could do a single loop and then just multiply by 8. Or we could do the whole thing, the whole circle. Now, remember that with these curves, if you have a curve, a Rose curve, if you have a Rose curve that has an even number, then from 0 to 2 pi traces out the curve exactly once. But if the coefficient of theta inside the sine or cosine is an odd number, then you will trace out the curve twice. And so you would have to, if you did the entire curve, you'd have to divide the whole thing by 2. So let's go ahead and do this one. We have, let's see, so I'm just going to do it with, let's see, f of theta is 5 sine of 4 theta. And then alpha is going to be 0 and beta is 2 pi, with the caveat that if this was a rose curve with, say, an odd number of petals, you'd have to divide by 2. Okay, so let's set up the integral. 1/2 0 to 2 pi 5 sine 4 theta squared. So you can probably guess that we're going to have to use the power reducing formula again. So let's scroll back up there and find that. There it is. There it is. The sine squared is 1 minus the cosine of 2 times the angle that you had divided by 2. So notice that's sine squared of theta. Since I have sine squared of 4 theta, I'll just change that 2 theta to 2 times 4 theta. So let's go back. Okay, so this thing is going to be 25 halves times the integral from 0 to 2 pi of 1 minus cosine of 8 theta. That's 2 times 4 theta, all over 2. Now we can do this pretty straightforward. It's not bad. 25 fourths times theta, that's the antiderivative of 1. The antiderivative of cosine of 8 theta is sine of 8 theta over 8. And this is evaluated from theta equals 0 to theta equals 2 pi. Here again, this one's pretty easy because the sine of 2 pi is, or the sine of 16 pi is 0, and the sine of 0 is 0. So this is going to equal 25 fourths times 2 pi minus the lower limit ends up being 0. So the final answer here is 25 halves pi as my area. Okay, excellent. So in the next video, we'll deal with the intersections in polar coordinates because that's where things get a little bit more dicey. So I avoided that on this rose curve here. There we go. I avoided the whole question of intersections by just saying that I'm going to do the entire curve from 0 to 2 pi. But it might have been better had I wanted to do the intersection to find out where this thing crosses the origin, and then from that figure out, figure out my limits from that. Okay, so see you in the next video.